Alright, so as I promised you, I made a video to finish up chapter 1 with an introduction to taking vector products and scalar products. So basically, these are two operations that we do with vectors. You're going to look at them and say, well, it's kind of like multiplying vectors. And in some ways it is, in some ways it isn't. I like to think of it more just like two different mathematical operations that we can do with vectors. Both of these operations have other names, and so I put those in parentheses. I often just use the other names, the ones that are in parentheses, so a vector product and a cross product are the same thing, and a scalar product and a dot product are the same thing. The cross and the dot come from the symbol that's in between the two vectors, which you'll see in a few minutes, and so it makes sense, so that's good. So the first thing that we're going to look at is what we call the scalar product, or of course the dot product. And when we talk about the dot product, you can see there's the dot right there, and when we're taking the dot product it looks like this: the vector A dot vector B. Now, the other name for this is the scalar product, and that's because the result of what that you get when you do this operation with two vectors is you get a scalar. So the result of this operation is a scalar, which means it only has magnitude, it doesn't have any direction. Now, how big is that magnitude? Well, right here is the expression that gives you the magnitude you get when you take the dot product of two vectors. It's equal to the magnitude of the two vectors multiplied by each other, and then times the cosine of the angle between the two vectors, which here we're calling phi. People have asked about how we name angles, and the book is choosing to use phi. We don't want to put too much importance in that. Other names that we give for angles are theta, alpha, and beta. And so if I put that in here as the name, it doesn't change anything. So don't get too hung up on the name. Notice, how do we determine this angle phi? If we put the vectors tail to tail, it's the angle between the two vectors then. So trying to sort of make some sense into, what are we doing? The dot product is going to make a lot more sense when we see an application of it, which is going to be when we see the application of work in a later chapter. But right now we're just sort of looking at it from a mathematical point of view. But we can use some of the information we learned in this chapter about vectors. And notice that since we say that this is what the dot product is equal to, we can think of it as the magnitude of A, but then the rest of it, the B cosine theta. Notice that if we take the projection, or the component of B that's parallel to A, which would be B cosine theta, because remember, this would be the adjacent side to the angle. It's like taking the magnitude of one vector times the component of that other vector that's in the direction of the first one. So you're taking one vector times the component of the second one that is parallel to the first vector. So we can also look at it in a day. We can also switch it around and think of it as the A cosine theta, which would be the projection of A onto B times the magnitude of B. Doesn't matter which way we do it, it's the same thing. And while we're at it, we are going to mention that the dot product is commutative, which means that if we switch the order of the two vectors, we're going to get the same answer. Nothing's going to change. So the scalar product can have positive values, negative values, or it can be zero. It all depends on what the angle is between the two vectors. Basically, if the angle is an acute angle, that is that it's somewhere between 0 and 90, then b cosine theta will be a positive value, and so you'll get a positive value of a dot b. So in this case, a dot b will be greater than 0. We have a situation where the angle between the two vectors is obtuse. Notice here, this angle is bigger than 90 degrees. Then the projection of b onto a is actually in this direction. It's in the negative direction. So this is a negative value. And so then when we multiply the two together, we get a dot b is going to be a negative value. And then finally, if the two vectors are perpendicular to each other, then because we're taking a times b, so we'll kind of write it like this, emphasizing that we're taking the magnitude times the cosine of 90. Well, the cosine of 90 is 0, so the dot product is 0. And that's because when we're thinking of it, the component of one of the vectors in the direction of the other one is 0, so that if we do a projection of b onto a, we just come right back down to the tail of a. We don't have anything that has any length. And so that's why, another way to think about it, why it's 0. So using sort of this definition, I might have a situation where I have a vector a, and I'm going to say that the length of this vector, I was going to say that's 10, and then I have a vector b, and I'm going to say the length of this one is 15, and then I'm going to call this angle here 40 degrees. So this is just, you might be presented with a situation like this and asked to find the dot product. So a dot b, remember we would take the magnitude of a times the magnitude of b times the cosine of the angle between them. Notice I use theta here because it doesn't matter what I call the angle, it's just the cosine of the angle between them. So this is then 10 times 15, those are the magnitudes of the two vectors, times the cosine of 40. And the answer then I would get is 115. So that's a very simple example of how I can find the scalar product. But remember that yesterday we talked about unit vectors, using those to write a vector. And so we have to be able to also figure out how to write the dot product or how to calculate it if I'm giving the vectors in unit vector form. You might think that it would be easy to figure out, well, I can figure out the angle between the two vectors. But guess what? If they have 3 components, it becomes pretty hard pretty quickly. And I think that you're going to not want to do it. So here in this situation, vector A is being written using the x unit vector, which is I, the y unit vector, which is j, and the z unit vector, which is k. Same thing goes with v, b. And so if we want to do the dot product, you can literally think about multiplying all these factors out so that, like, I'd have to multiply this times this and this times this, etc. So let's start writing down all the terms I would have. So I have ax, bx, and then we can't forget, I'd have I hat dot I hat, then ax, by, I hat dot j hat, plus ax times bz, I hat times k hat. And we're going to keep on going. So you might say, wow, this is a lot more than I see up here, so what's going on here? So you have to think about, when I'm doing these, are there any reasons why some of these are going to go to 0? So we have a lot of different, dot products, and we have to see if we can figure out what we get when we're taking the dot product of unit vectors by each other. So let's remember what the dot product, A dot B, is just the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay, so for instance, if I have I dot J, how would I figure this out? Well, the magnitude of I is 1 because it's a unit vector. The magnitude of J is 1 because it's a unit vector. And then I have to think about what's the angle between them. Well, this is in the x direction and this is in the y direction. Those two axes are always perpendicular to each other, so the cosine of 90. And so cosine of 90 is 0, so this answer would just be 0. And I would do the same thing if I did I dot K. I'm still going to get 1 times the cosine of 90 is 0. So what we're going to quickly figure out is all the mixed dot products of the unit vectors are 0 equals 0 because they're all perpendicular to each other. But if I do I dot I get 1 times the cosine of 0. I just get 1. And the same thing happens if I get J dot J. I get 1. And K dot K equals 1. So, working back, all the mixed products of those two vectors, all the terms that are mixed, like an x and a y, those vanish, and I'm only left with ax, bx, I dot I, plus ay, by, j dot j, and az, bz, k dot k. And these are just 1. All these terms are just 1. And so, really, that's how we get that result, that when I'm taking the dot product of two vectors written in unit vector form, I just multiply the like components and add them all together. Which is the result that I had originally. So hopefully that makes sense. Again, people seem to be a little outraged about the whole idea of these unit vectors, but they're really easy to work with, and this is a really easy operation. So at an example, if I have these two vectors written in unit vector form, what is A dot B? Well, A dot B, I'm going to take the x component of A, which is 3, times the x component of B, which is minus 8, and then add to it the y component of A, which is 4, times the y component of B, which is 6. So I'm just going to write these ax, bx, ay, by. I get minus 24 plus 24. Actually get 0. You know, it doesn't always happen. But then you can say, what does this tell us? If you remember, when I take two vectors and take their dot product, and if I get 0, that means they're perpendicular to each other. So I actually learned even more. All right, so now we're to move on to the vector product, which is also called the cross product, and that's because of this little symbol here. So when I do the vector product or the cross product, the reason it has its name vector product is because the answer is a vector. So we need, oops, we need to find two things. We need to figure out the magnitude of C, and we also need to figure out its direction. Because it has both, because this is a vector. The first thing that we do is the magnitude, and you notice it looks really similar to the dot product, but we take the sine of the angle between them, of the two vectors when they're put tail to tail. You can't just interchange them. It's important that it's the sine, and so you do have to remember that that's how we find it. And so that is pretty straightforward because we've done a little bit of this already. The thing that's tricky about the cross product is figuring out the direction, because we use what we call the right hand rule. There's a couple different ways to do the right hand rule, and so if you aren't comfortable with what's shown in your book, you can always Google it to see if there's a method that works for you. I have a method that works for me, and I stick with it because it works. And so the general idea is I think of the two vectors that I'm taking the cross product of. I think of them going tail to tail, and then I lay my hand along the first vector, pointing in the direction that that first vector points, and then I curl my fingers towards the second vector. Now, it turns out that your fingers only curl one way. That's the way your fingers bend. So if you can't curl your fingers in the direction of the second vector, you need to rotate your hand until you can curl in that direction. Once you've done that, your thumb is oriented like you put it up like you're a hitchhiker, and that's the direction of the cross product. And so here you see an illustration of that. Now, the thing that's interesting about this that you might not really immediately notice is that the cross product result is perpendicular to both A and B. Now, this question came up in the reading, but maybe you forget that two vectors will always define a plane. That is, I can always draw two vectors on a piece of paper. It doesn't matter how they're oriented relative to each other. I can always draw them on a piece of paper. And so that piece of paper is the plane that they lie in. But when I take the cross product of those two vectors, the result is going to be perpendicular to that piece of paper, either pointing up or down. And we use the right hand rule to figure out which way it is. Because of that, because it's really important that I start with my fingers pointing in the direction of the first vector and then curl in the direction of the second vector, this is not commutative. Like we saw the dot product was, but it's not because there's this negative sign. You would still get the same magnitude when you switch up the vectors for the cross product, but you get an opposite direction. And there's another picture sort of illustrating in both of these situations that the third vector is perpendicular. So here's our original picture we were just looking at. Here's another problem where vectors A and B are actually in the xy plane, and then showing that vector C, which is equal to A cross B, is actually equal to, or is perpendicular to both of those. And so if we had if we had a value for A, we'll call this one 15, and this one 10, the magnitude of A cross B I could find would be 15 times 10 times the sine of 30. The sine of 30 is a half, so this is going to be 75. And then we see the direction of this is in the z direction. I actually did another video of how to calculate the cross product with the unit vectors, and I really encourage you to watch this. You are going to have to know how to do this eventually. So watch all the videos. that I put up for you today. All right, and that is it for vector products and dot products.